Welcome to Easy Mathematics and a new video. Today we take a look at two integrals from the MIT Integration Bee 2021 from the Qualifier sheet. And the first one looks like this: x sine x over 1 plus cosine squared of x. And the second one is a easy polynomial, I would say. And for the first one, a couple of months ago I saw a video from Michael Penn, and he proved this lemma. And when I saw this integral, it reminds me of this form. We have here this x and then a function of sine, and remember, cosine squared is also a function of sine. So this reminds me of this left hand side. Also the borders are the same. So if we have x times function of sine, we can rewrite this integral with the same borders, pi over 2 on the front, and then get rid of the x. Alright? And we will see that this will leads us to our goal. And I want to recall the derivative of the arctangent, 1 over 1 plus x squared, and we see here 1 over 1 plus something squared, and also the derivative of the cosine is minus sine, so there is some chain rule going on. So this will leads us to the goal. And the second one, it's an easy polynomial. You can integrate each part of this each part of the sum, and then plug in upper bound and lower bound. But there is obviously a trick. And if you want to try this by yourself, take a look at the coefficients. These should remind you of something. We will see this in a couple of minutes. Okay, so let's start with the first integral. And like I said, we have here our x and our x, and the rest of it is a function of sine, so we are good to go. And so we can rewrite the first integral as pi over 2 integral 0 to pi sine x over 1 plus cosine squared of x, and I put a minus here and a minus here. So we see that minus sine is the derivative of the cosine, so here's an inverse tangent going on, and this leads us immediately to pi over 2 times minus inverse tangent of cosine x from 0 to pi. And if you evaluate this, I leave that to you. This is the pi over 2 stays here, and this part, it gets also pi over 2, so final result pi squared over 4. Alright? So the last details, I leave that for you, it's not so difficult, and the result is pi squared over 4. And for the second integral, there is obviously one nice trick, and we see that the exponents, they are decreasing by 3 from left to right, and we have no constant term. Every number is nicely divisible by 3, so it makes sense to factor out 3x squared. And so let's see what we get. So we put 3x squared outside, cube root 2 up to cube root 3, and then we are left with x to the 12th minus 4 times x to the 9th plus 6 times x to the 6 minus 4 times x to the 3 plus 1 dx. And now, if you open your eyes, these coefficients 1, 4, 6, 4, 1, this reminds of the Pascalian triangle. Pascalian triangle, yeah, with alternating signs, and so we get integral from cube root 2 up to cube root 3, 3x squared times x to the power 3 minus 1 to the 4th dx. Alright, yeah, you can check this as, so you can check by yourself that this is correct. And now what we immediately see, this part is the derivative of this part, so we can nicely integrate this. So the new exponent is 5, so we get 1 over 5 x cubed minus 1 to the power 5 from cube root 2 to cube root 3. And then if we plug in upper bound, cube root 3 cubed is 3, 3 minus 1 is 2, so 3 minus 1 to the 5th over 5 minus 2 minus 1 to the 5th over 5, so the final result is 1 over 5 times 2 to the 5 minus 1. Yeah, this is the solution to the second integral. And yeah, like I said, here of course there is some nice trick here going on, and these numbers 3, 12, 18, or in other words this pattern 1, 4, 6, 4, 1, this should remind you to the Pascalian triangle. And here we get a nice derivative of the inner polynomial, so we can nicely integrate, and yeah, the cube roots, so the cube root get cancelled with the cubed here, so we get a really beautiful result. Yeah, and these are the two integrals. I hope you liked it. Thanks for watching, and I leave the link, the lemma from Michael Penn, in the video description, so you can check this out. See you next time. Bye bye.